Welcome to this very awesome tutorial. Today we will be tackling from PyTorch model training and data processing and all the way to deployment in a Flutter app. So first of all, let us begin with the training pipeline. So of course we import the libraries that we need. Then after importing the libraries that we need, we're also going to import dataset and data loader. After that, we're going to import reduce and default date to get the countable and trainable parameters from our model. That's the PyTorch model. So the next part is going to be the configuration part. We're going to define the things we need. That's like the seed, the labels, the device. For me, it's CPU, the batch size, and the image size. Then the epochs. So we're going to then set the seed for data reproducibility. So of course we're going to set seed for OS, NumPy, and Torch, both the CPU and the GPU. That's the cuDNN library. Then we are going to call that function to set the seed. Then the next part is to import the paths to the image that we're going to use. That's the dataset. I'll append the link below. Then we are going to split them. Then we get 75% train images and 25% test. So let's now define the data loading pipeline using the PyTorch dataset. So first of course, we have to define the transforms that we need. For training, we're going to get 4 transforms. That's to tensor, normalize, random horizontal flip, and Gaussian blur. For the testing, we're going to get only 2. That's to tensor and normalize. Now let's define our data loading pipeline. Of course, we initialize the things that we need. That's image path, training, image size, transforms. Then we are going to, this function is actually used during the data loading stage implicitly. So that one I'll skip. Then get item, we're going to get the image path. We're going to read it in a function that we'll define below. And then if it's training, we also get to extract the label from the image path. Else we're only going to return the image if it's tested. Then in the read image, of course, it reads the image, converts it to RGB, then resizes it to the required size, then applies the transforms to the image before finally returning the image over here. Yeah. So the next part after that is now to define the data loader for batch processing and using workers in a CPU and GPU. And so we're going to, of course, load the train and test data, and then we're going to use the data loaders to make use of batch processing, and then after that we return the data loaders. So we're going to use the first batch of the images and labels from the trained data, which we're going to visualize. So before we visualize, of course, since we did a normalization, we'll have to inverse norm, which is to reverse the effects of normalization. Yeah, after doing that, now we can visualize our images. So we look through the images and labels. We'll show them in a 4x4 grid. So of course, we show, first of all, we permute, which is to inverse the effects of the to tensor, the first half of the effects, because to tensor permutes and then divides by 255. So we permute, of course, the inverse norm has done the multiplication by 255. So we have no problem about that. We're going to visualize the title based on the labels and then set axis off before finally showing the whole grid of the images. Now we want to build the whole model. Of course, we're going to use transfer learning. So we download a pre-trained model. Then we set the parameters to false in order to freeze the weights of the model. And then after that, now we modify the classifier layer of the model by now putting our own layers. So in the input, the output 64, then we pass it parallelly, then drop out. So we repeat the same. And then of course, then the last part is now input of 10, then the output of 1. So after now defining our model, now we can get to count the number of parameters. That's the trainable. We also get the total parameters, and then we can print the trainable parameters over the true parameters in the model. The next thing, of course, now calling the function does that. The next thing is now to define the metric monitor. Yeah, so we get to define the metric monitor. Of course, in it we'll reset the object to 0. We'll reset the values to be tracked. That's the object to be 0. That's the value, count, and average. So reset will set them to 0. Then update ensures the values are updated during training. So that's the values to be updated are val, count, and average. Yes. Now the string which will be printed during the progress of training will print for every metric that will be updating, will be printing the result. Yeah, so that's how it is. Yeah, and then the next part now is to initialize our criterion. That's our loss function. That's we're going to use the binary cross entropy with logits because we have not used any activation function in the output. Yeah, we're going to use the stochastic gradient descent for the optimizer, and then we are going to now bind the model to maybe the CPU, the GPU that you're using, and then after that we define the calculate accuracy function, which will get the output from the model, and do the sigmoid, get the boolean whether it's above 0.5 or below, then of course convert it to a true or false. Then after that we're going to, so this, yeah, after that we're going to get the positive over the total. So after that now we define the train. So we initialize the metric monitor, then we ensure that we set the model to train, then we say we initialize the progress buff during training. So we look through the images and targets. Of course, the train loader will already be here now, and then for every image we set it to the device that we're using, either GPU or CPU. Then the equivalent goes for the targets, of which we do that after flat, and then we flatten, and then after that we get the output from the images. We calculate the criterion, then we of course calculate the accuracy, then we update the metrics that lost accuracy, and then we set the gradient to 0. We propagate the loss to the model, and then we update the weights of the model, and then of course we print the results. So this line that I did is actually when you want to get maybe one single batch, or maybe 2 batches for you want to use a sample for training and you don't want to use the whole data, so you will have to use that line. So the next part is now to create the loop for training. So for every loop, so we saw that this one was 3, so we are going up to 3 epochs. So for every, if you want to save maybe the model after every 10 epochs, you can do that. And then yeah, so that's it for the PyTorch from data preprocessing all the way to model training and model saving. So the next part I'm going to talk about inference. So in the inference pipeline we are going to implement it. So first of all, of course, we import the layers that the libraries that we need. So after doing that, we then set seed. Of course, define configurations, then set the seed that we need. That's OS, NumPy, and the touch seed. And then we call it to set the seed for data reproducibility. So again, now we load our data, but now the paths is what we actually need, for which these paths you can reproduce the test dataset from the last part that we have done, that's the training pipeline, in order to run predictions of the inference model through the test data. But I will not do that here. We just get the variable, the test data from the last part, and you can run the inference. So for this parts, I'm going to save the paths since I'm going to use it in the Express server to run the server. So yeah, to test the mod on an Onnx model. So now we create an inference model for which almost all the preprocessing pipeline will be embedded in the model in order to not have so much issue while porting the model to mobile or web. So it's always recommended to do that in order to have as few complexities as possible during porting. So the only thing that we'll do is actually when converting to Tensor, that's the only thing that we'll be doing, because everything else the processing will do here. So like, of course, the init layer will initialize the model, and then in the forward part, we're going to get the transforms, and then we get the access the transforms as a layer. Then after that, we pass it to the model, and then we return it. So the transforms bit is actually the one where we are going to define some many processing. So we are going to define a custom processing which does a permute and a divide by 255. So if you recognize well, this is the two tensor transforms. Yeah, so after defining that bit, we are going to unsqueeze it in order to introduce batch dimensions. And then if it's training, we are going to do all the other transforms related to training. That's the custom to tensor, the normalize, the random flip, and the Gaussian blur. So otherwise, if it's testing, we're only going to do the to tensor and the normalize. So after that, we're going to, since we saved the model last, so this is model I trained on Google Colab. So after that, we saved it. I'm going to load it. Then after loading it, I set it to evaluation mode, and then I load it into inference mode. Then for the test data, now that you have gotten the code from the last part, that's the last part that was just concluded, you get the test data, and then you can run inference in this way. So you get the output, we convert it to sigmoid, and then of course after that we show the image, and then we get the title, and then we print out the title, insert axis off, and then show the all grid. So that's how you do the inference with the inference model and the test data set. So after that, now this is the code, now the touch code that will export our in model from PyTorch to the next model that we'll be using now in our Express server. So for the inference server, of course, I'll be using Express. So first of all, of course, you have to use Node in order to download the libraries, and also to download Express, of which we're going to use Express. But for now, I'm going to run the Onnx model locally through some files. So let's start. So of course, using npm init, you'll create a new app, and then in the package.json, you'll go over here and you introduce type module. Yes, and then the packages, that dependencies that I'm using are these ones. I'll link all these files to a GitHub repo where you'll have all the access. So after that, now we get to use import and require. This type module helps us to use both import and require in the same file. So we import our libraries, of course, then we get to import the libraries Jimp and model path, file system, and port in the app. So then after that, we're going to load the model. So we're going to load the model. If it's present, return it to the caller function for the main, else show the error. Of course, the ORT is enabled by this library, the Onnx runtime node. So after doing that, we're going to initialize our paths variable, of which now we are loading our model into the session. So to get the inputs and outputs of the model, which I'm going to show you later where we're going to use it, you just print session, you console log session, and then you get the inputs and outputs of the model. So we actually are going to randomize the paths using the Stateful shuffle algorithm, which is a modification of the fish, yeah, the Fisher Yates. So yes, so this shuffle function actually just shuffles the paths every time we run this file in the command line. So this is how the function looks like, so you can go through it and understand it better. Then we return the array after it has shuffled through the paths. Yes, so now after that we're going to now load the paths from the test paths.txt, which of course we saved in the previous part of the series. And then we split it in order to get the paths per line, and then of course we shuffle, and then we get the first 16 images since these are the ones that we want to predict. Yeah, so else we catch the error, of course, and then we now write the asynchronous function for predicting the images. So this one will go through we go through the paths in a loop, and then for each loop we call this function. With the function now we get the data. Then after getting the data, we'll have to flatten the data, of course. So we extract the R, G, and B channels from the image data. So we loop, and then we get the R, the G, and the B channels, and then we forgo the alpha channel because we don't need it. So and then after that we convert it to a float 32 type. Yeah, so float 32 type. So since the Onnx model requires a float 32, so we're going to use float 32. Then we convert to a tensor. Of course, we want 224 by 224 by 3. Of course, since everything in the preprocessing, including but the permute and the introducing batch dimension and normalizing is done in the model, we don't need to now start with the 3 since that PyTorch starts with the 3. Let's say it's always 1, then 3, then 2 to 4 by 2 to 4. That's the way PyTorch input is. But since we've done every processing inbuilt in the inference model, we don't need to do that. So we pass the image as it is. Yeah, so after that, now we print the model input and output. So the model input and output is used in this part. Now you have to represent the model input here as the key here. It's a must for it to work. And then of course you run the input through the model, and then you get the output here. Now this for 86, when I printed it, the input was this one and the output was this one, so you have to use this one. So and then I use the sigmoid. Yeah, so then I get the predicted output. Then I, of course, now I want to compare it to the correct output and the predicted. So predicted output, I get that way, and then of course I use the unary operator to convert its operand to a number. So if predicted is equals to correct, we print the label in as green, else we'll print it as red. So we'll now define the inference pipeline where we look through the images. We read the images using the Jimp library. As this is, I just did because my path for the folder for the images is a bit be in a parent folder. So I read the image parts, then after reading I resize it, then after resizing I call the predict image. So and then after that now we run the await inference pipeline to run the inference to the images. So let's do that in command line and see how it is. Okay, so before I go to the terminal, there's a line I've added, actually line 62. I've added it in order that we may print the model, and so then we can see the inputs and outputs, so that if you build your own, you'll be able to get them. So yeah, so like now we are going to switch the terminal that we're going to use. So yeah, so here in the node folder, I'm in the node folder which contains our file. Of course, like we can get to see that it's the file. There's the line that we added. So yeah, so To run it, we'll have to use node apply.js. So this one I'm now using. I'm running now the model on local images. So yeah, it was actually printed on every loop, but it's okay. So we see, like, if we print the input is this one, the output is this one for the model, then this is the prediction. Of course, we see it's a cat, so it's correct. It's a cat, it's a dog. Yes. So now if I go ahead and remove it, and so then let's run it until we get maybe a wrong prediction. Yeah, so cat, dog, yeah. Running again. Yeah, we see that there's a wrong prediction. Yeah, it's a dog, but it's predicted as a cat. Yeah, so that's how we can run it local. Now on the server part, I just did, everything is the same. Everything is the same. I only introduced body parser and express file upload. Express file upload enables us to get access to. Okay, actually, I did not use this one because I read it as a base64 image. So this was the backend for the Flutter app that I built. So I used body parser because in order to get the contents of the request.body for the express, then yeah, so this one I did not use it. So everything is the same. Of course, the predict image is the same as the other one. This is the one for loading the model, the Onnx model, and everything is the same here. Actually, the only difference now, I'm returning the predicted output. I'm not consolidating it. So when this is the image resizer, so whenever an image is sent in the post route predict, it gets the image from the body. Because it's encoded in base64, it will be part of the request.body, not now the request.files. So and then we convert it now to the image, to image file. Then we pass it through the image resizer, that's the Jimp image resizer, to convert it to the image size that we want. And after that, we run the prediction, and then we get back our prediction. I was logging it, but then now I'm sending it back to the Flutter app. Yeah, so and then we start the Express server. So this is now the Express server, and now we go to now the last part, which is the Flutter app, and then we finalize our deployment. Now we are on to the last stage, which is the Flutter app. So I want to talk about the Flutter app for now. So yeah, when you create the Flutter app, the libraries that I'll be using are this is an inbuilt material that they use the provider for state management. We use the image picker to pick images. We use IO for files. We use convert for JSON encode, and HTTP to send requests to the Express server. So before I continue on further, I want to go to this file, pubspec.yaml, and show you that these are the libraries that we'll be using. So whenever you just put them libraries here, they'll be installed using Flutter. If you run Flutter pub-get, or will just be automatic. Yeah, so you put the libraries here and it will be automatic, then you import them here. So one thing, for the state management, which I want to talk about, we create a class here which will change data, and then that data can be accessed from anywhere. So this notify listeners whenever the change image state is executed. Let's go to the save image part. So whenever we call the open image picker function, then the open image picker function will get the context to the change image state, and then call the save image function, and then the save image function will now run, and when it runs, it will execute and then notify listeners, and then these listeners, we can now get to listen to the events of the of the class, maybe from another pipe, let's say like here. Yeah, we can now use a consumer to get to listen to the notify listener, and then when it listens, then the data will be reactive. So I use the state management because the button here which loads the image and the show image with widget here are different. So in order to get to have the data being reactive across different widgets, you'll have to use a provider in order to do that. So yeah, so let me then talk about stateless widgets. So in Flutter, stateless widgets are widgets that constantly change state, like this widget, since this change state whenever a response is received. These are stateful widgets. Yeah, so this is also stateful because this button, the button initiates an action on press. This one is also stateful, but now this black background is stateless. So you can encapsulate stateful widgets in a stateless widget. Yeah, so stateful widgets change state over time, but stateless don't change state. So yeah, so in my app, this is the general app itself. I have used safe area in order so that this app might not go up to the upper part of the screen. Yeah, so we call a component my home page. Now this my home page, it actually has the show picture part and the button action part. So the show picture part occupies 2/3 of the screen because it has 2 times the in size as the button action. So for the show picture, we know that it's actually a stateful widget because the image will change. So we'll initialize a stateful widget, and then in the stateful widget, we'll be listening to the change in the action. Yeah, so first of all, we will this data.image is actually null. So if I go here, the image is actually null. I've used the let to tell Flutter that it will be initialized later on, but for now it's actually null. So because it's null, the 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 data loaded is also initialized to false. Yeah, the data loaded is also initialized to false. So because it's false, it will actually render now this fun dog that we have here. But when now the image is loaded, it will convert it to true, and then the notify listener will trigger change, and then the consumer will ensure now the widget becomes reactive and then shows our image there. Yeah, so after loading the image, yeah, so the button action part just does the thing for us. It gets to call this this function, which is an asynchronous function, since it returns a promise, which of course I've awaited here, and then of course yeah, so after that I get the picked image and I save it as a file, of which now we go to the notify listener. So the button action, the image is called yeah, so it's called so this part actually helps us to change this one if it's a dog predicted or a cat predicted. Yeah, so I'll save all these in the GitHub repo so you'll have access. So the image search is that one, then the cat part this side is this one, also has a consumer widget, and then yeah, so whenever an image is loaded, we'll call the image open image picker function, and then this open image picker function here will pick an image from gallery, and then get call the change notifier, the class we've extended with the change notifier, and then we save the image as a function, then we notify the listeners. Then of course, whenever after we've notified the listener, what we'll do now inside yeah, inside here, yeah, after getting the image, we'll now call this function, which of course, because we are receiving the image as a base 64, so we get the image from the front end, from the Flutter app, we encode it, and then we send it over the HTTP request. So now if I start the server, yes, so it will be running on port 8085. Okay, and then the reason I've used the network address is because the local address conflicts with the address that this app is run. The app is now running, so you need to use the network address. So it's listening on port 8085. Yeah, so that's the same. Yeah, so after sending the image, we see that now on the back end part we'll get the image, decode it from base 64 now to the image, and then get the predictions and then return the prediction. So the returned prediction will actually, now we go up. Yeah, so the returned prediction will be returned as a response. Now we get the body from the response, and then we get a boolean, is cat true or false. So if it's true, then we go back here, to this point. So if it's true, if the prediction is true, this is a dog part, so the cat part will be thumbs down. So it will be thumbs down because if the prediction is a cat, else it will be thumbs up. So it goes the same for the color, so it's icon color, and also for the cat is after. Yeah, so the cat is also after. Yeah, so that's how. Let's do a sample image. Let me download an image from Unsplash, so that we can not use any image from the dataset that we now let's do inference and see how the front end, that's the Flutter app, will react, and also how the backend, which is still running, will be. So it's that. So we go over here, click here button, we pick an image, and it will run, and we will predict a dog. Nice. So we see that the backend, since we were console logging it, if you noticed there was a console log, so it's okay. The front end is okay. Now if we do the cut, also go here, click the cut. Yeah, we see now the cut has been predicted. Okay, and another thing which I wanted to talk about, which I almost forgot, is there's an XML file where, in order to use the HTTP request, you'll have to include this line. So the Android manifest XML file is actually in you go to Android, you go to app, you go to source, you go to main, and define the Android manifest.xml file, and you add it here so that you can be able to use the HTTP package for Flutter. Yeah, so that will be all for the series, which is from PyTorch data processing and model training to deployment in Flutter app. So thank you all. So next time I'll be handling object detection algorithms, and I'll be focusing on the YOLO version 4, YOLO version 5. YOLO version 4 is for TensorFlow, 5 I'll be doing with the PyTorch. I'll also be talking about the PyTorch video library.